So let's quickly go through the important aspects of Young's double slit experiment, or what we generally in short just call YDSE from this point onwards. So this arrangement of YDSE is very important to understand. You have two opaque screens, and then you have an observation screen on which you observe the fringe pattern at a very large distance away from this. Okay, so the primary source of light, which is monochromatic, is over here. Suppose it is generating wavefronts like this, which is of single wavelength lambda. So what is going to happen is that the different wave trains going in different directions, so they are all of same wavelength and therefore same frequency, they're not going to be coherent because they are generated randomly at different times. The phase constant randomly varies with time. So even though the rays, the so-called waves, the electromagnetic waves or light waves, they are of same frequency and wavelength, they are not coherent even though they are coming from the single so-called point source, because what we are seeing as a single point source, within that there are actually literally infinite number of atomic level sources which are all random in phase. So that is the problem with that is the complication when we are dealing with electromagnetic waves or in particular light waves. It's difficult to generate coherence from atomic sources like that. Okay, but that problem of difficulty of generating atomic, generating coherent light, that was solved by the genius of Young, really, and by making use of, in other ways, just a practical application of Huygens principle. And that practical application is that you have this kind of arrangement here, that you have two slits which are symmetrically placed with respect to the single slit here, and the single slit now illuminates these two symmetrically placed slits. Okay. So this is the concept. So we had seen that as a wavefront hits the screen, the few of the so every point on the wavefront acts like a secondary point source. So if this slit is narrow enough, you can more or less treat the slit as a single secondary point source. So that starts generating wavefronts in this direction here. So these waves now are going to be coherent. They are going to be coherent and monochromatic because they are coming from a secondary monochromatic point source instead of coming from a collection of atomic primary sources. So that is the principle. So then the wave reaching S1 and the wave reaching S2 are coherent. And not only that, they are in phase because they are traveling the same distance because they are symmetrically. So that creates light on this side from S1 and S2, which is monochromatic and coherent. So that is the main thing. Okay? And rest of the thing was just about the geometry. So the distance between the two slits was d. The distance between the slit and the main screen on which we are observing the interference pattern was capital D. And we always arrange it such that capital D is very large compared to small d. So capital D will be typically of the order of few meters, and small d will be of the order of millimeters, whereas the wavelength of light is of the order of 100 nanometers, 400 to 700 nanometers. That is the visible light's range of wavelength. So basically, that is the arrangement in a nutshell. So you can see that light coming to the symmetry point on the screen is with zero path difference. So there we get constructive interference with zero phase difference. So that is called the central bright fringe or the central maxima. Whereas in general, if we look at any arbitrary point, which you can say is at an it is at an angular position of theta, okay, or at a linear position of y with respect to this origin here, you can see that light reaching there will have path difference and therefore phase difference. So if we take any arbitrary position, which is at an angular position theta or at a linear position y, see that the path difference delta x, which is S2p, this point is p, minus S1p, is approximated to d sine theta under this condition, which is further approximated to d tan theta or d into y by d. This becomes the path difference. Okay. So there is also another interesting way of deriving this path difference, and we had seen the geometrical method last time, but we can also use a combination of binomial approximation kind of concepts that we have seen earlier in sound also. So if you just concentrate on this part of the experimental setup between the two slits and the screen, keep in mind that capital D is large compared to small d. Okay, so if we take this angular position as theta, we can also use trigonometry, a little more sort of sophisticated way of calculating this path difference, and from that the phase difference. So if you name this central point C, now let's take the distance CP as Z or something, which is square root of y square plus d square. And you can also see here that this is d by 2 and this is d by 2. So if you look at triangle CS2P, okay, that one. So in that you can see that this total angle, this angle S2CP is pi by 2 plus theta. So in that now the distance S2P, or what we can write as x2, this distance is x2, let's say this distance is x1. Yeah, so this distance x2 can be written as square root of z square plus d by 2 whole square minus 2 times z into d by 2 into cosine of this angle, which is pi by 2 plus theta. So that's how this can be written as this much plus zd sine theta. Cos of pi by 2 plus theta we can write as this. Okay, so once we write this is this. Okay, so x2, now you can start applying the approximation. Now d is very small compared to z, so first of all x2 can be approximated this way, that you remove d square by 4 from the analysis because it's negligible. Okay, and then you take z common from this, so this becomes 1 minus, sorry, this will become plus, this is cos of pi by 2 plus theta with the minus sign outside, so it will become, so this will become this plus d by z sine theta to the power half. So that's where you can again bring in binomial approximation. It becomes z into 1 plus d by 2z sine theta. This is your x2. Now similarly, if you do an analysis in triangle S1CP, So by the same kind of steps, right, you will get x1 as square root of z square plus this minus 2 p by 2 z, but this time it will be cos of pi by 2 minus theta. So you can see that in this triangle, angle S1 CP is actually pi by 2 minus theta. It's an acute angle because you've taken the point P above the point O. So with the same steps now, you will get x1 with all the approximation as z into 1 minus p by 2 z sine theta to the power half. So now you look at this expression and this expression and you calculate the path difference by subtracting the two. So you can just go through this once if you like. So this is the formula for path difference at P. So delta x, which is x2 minus x1, becomes d sine theta, which we can further approximate as d tan theta because we are taking y to be small compared to capital D also. So we are not going very far off on the screen because remember capital D is of the order of meters. So if we are within a few centimeters range of the symmetry point O, then this approximation is correct that y is very small compared to t. So in that case we can substitute sine theta as tan theta and that becomes dy by d. So the path difference in terms of y such that it's directly proportional to y, or in terms of theta it is proportional to sine theta. So ultimately in YDSE, this is the most important expression at the end of the day, this one or this one. Along with this, there are a few kinds of tricks that we need to apply for understanding the calculation part in some variation type of questions. But apart from that, in terms of wave analysis, it's very simple. It is just about the interference formula, path difference to phase difference, and from phase difference, how to get the amplitude or the intensity. Okay, so before we proceed further, let's also understand how this whole arrangement looks three-dimensionally. So basically, S, S1 and S2. Oh, just a minute. You can note this down. Yes. Okay, so as I was saying, this is the final equation which is important for you. The calculation of delta x in terms of either y, the linear position of the point P with respect to the symmetry point, or the angular position theta. Okay. Now, let's understand the geometry of this arrangement a little bit better. So, these three S, S1 and S2 are basically horizontal strips we call slits. Okay, that is, so a slit is basically like a thin, a longitudinal cut or gap such that, now this is important, the slit width W, that W is of the same order of magnitude as lambda. So for example, that slit width will be 2 lambda or lambda or something like that. Because if the slit width is too much compared to lambda, there is some additional complication that happens, and that is diffraction effect. And we will understand diffraction effect in more detail later. So if I want to look at this experiment or understand this experimental setup, it's basically like this, that so these are opaque screens, and this is the main screen for observation. So its front surface is white. It's a white screen. Okay. These are more or less blackened, but it doesn't really matter. They are opaque, so light cannot pass through them. And you have the monochromatic source on this side. So for example, it can be a sodium vapor lamp or bulb. Lambda is around 680 nanometers for that. So what we mean by the slit in front now is that this screen, it has a horizontal gap like this. So this is the single slit on this screen. And similarly, this screen in front of it now, this is the central point. There's these two kind of slits here. And this is of the similar width W. So typically in a standard Young's double slit experiment, both the slits have the same S1 and S2 should be of the same width and are symmetric respect to s. So the distance s1 is equal to the distance s2, or they are symmetric with respect to c. Okay. So now what happens? The light that escapes from this side due to the two slits, it interferes and it creates a pattern on the screen, which is like this. There will be a bright intensity, then it will be kind of darkish, then again bright. So we will see like bands of light, alternately bright and dark. So these bands of light, they are called the fringes, the interference pattern fringes. So we have central maxima, then the first minima, then the first maxima. So on the screen, what we observe, we observed light on the main screen. It is a pattern of alternate bright and dark fringes. These fringes are nothing but, like thin horizontal bands of light. That is the thing. So this is the three-dimensional arrangement. Okay. So once again, coming back to the side view of the main observation screen versus the two slits. Okay, Sudhir. I'll give you time to note this down. Don't worry. Okay. Just give me a second. So path difference. So was d sine theta or dy by d. Now, since S1 and S2 are not only coherent and monochromatic, but also in phase. The two sources S1 and S2 are in phase because they were equidistant from the single slit S. Okay, so for light waves at the point P, okay, from the two independent coherent sources S1 and S2, the phase difference, okay, delta phi is equal to nothing but 2 pi by lambda times delta x, because there is no phase difference between S1 and S2. So the only reason why there's phase difference between the light coming from S1 and S2 at the point P is that light coming from S2 is traveling a longer path compared to the light traveling from this, okay, or it is k delta x, that is nothing but 2 pi by lambda into x2 minus x1. So the formula for this phase difference delta phi becomes 2 pi by lambda into dy by d. So from this we can see that therefore for bright fringes, the general formula becomes delta phi is equal to even multiple of pi or 2n pi. So correspondingly delta x should be equal to 0 lambda 2 lambda whole multiple of lambda. So correspondingly we will get this formula now. We will replace path difference delta x with dy by d. So dy by d equals to 0 implies y equal to 0. This is the position of central maxima, okay, or what we call the central bright fringe, for which the phase difference is 0. dy by d or delta x equals to, now we can put it plus minus lambda because it could be above and below, corresponds to y being plus or minus of d lambda by small d. Okay. So this is the positions of what we call the first bright fringe, or what we can also call as the first order maxima. So this is above and below the central maxima. So at this point the phase difference is 2 pi. So it's that band of light which is bright right above or right below the central maxima. So it is at a distance of d lambda by d. Similarly, delta x or dy by d becoming plus or minus 2 lambda means y is equal to plus or minus 2 times d lambda by d. So this becomes the positions, or these become the positions of the second order, of the second bright fringe, what is called second order maxima, where the phase difference is 4 pi. And like that, delta x or dy by d being plus or minus n lambda, where n is a natural number, gives us this position above or below. So this is the nth maxima, bright fringe, at which the phase difference is 2n pi. So that is the analysis of the position of the maximas. So locations of bright fringes are symmetrically above and below the central maxima. So y equal to plus or minus of n times d lambda by d. This is the important formula. Plus means above and minus means below. So that final form. Okay, so just take you through this again. You can note down missed above also if you want to note this down. Okay. Okay, so these are the positions of the bright fringes. Now, similarly, position of the dark fringes. They are nothing but positions where the phase difference is an odd multiple of pi. So, dark fringes, they are the positions at which delta phi is of the order of 2n plus 1 or 2n minus 1, however we write it, odd multiple of pi. So correspondingly, path difference delta x will become either lambda by 2 or 3 lambda by 2, 5 lambda by 2, or like this an odd multiple of lambda by 2. So correspondingly, delta x, which is d sine theta or dy by d, it should be 2n plus 1 lambda by 2. So the position on the screen, the linear position y, will become an odd multiple of this factor d lambda by 2d. So this is the general formula. Actually, you know what, we will write it as 2n minus 1 because we will not start n from 0. We'll start n from 1 because there's no such thing as the 0th order or central dark fringe. We start from n equal to 1. So here n is equal to natural numbers. So n equal to 1, or what is called the first order minima, the first dark fringe. This is located at y equal to plus minus of d lambda by 2d, below the 0th central maximum. Or it is, you can also understand, it is right in between the 0th central maxima and first order maxima. So this is at y equal to 0. This was at y equal to plus minus d lambda by d. So basically on the screen what is happening is that this is your symmetry point O, then your central maxima is located here, your first bright fringe is located depending on whether you're going above or below. It is located like this. Okay, so this distance is d lambda by d. This distance is d lambda by d. Now your first minimas, they are located here and here. So this is the first dark fringe above and the first dark fringe below. So it is located right at the symmetry midpoint of the central maxima. You can see this is d lambda by 2d. So it's located right in between the central maxima and the first order maxima. So, so they're like equidistant bands of alternately bright and dark light. Similarly, n equal to 2 or second order minima. So they are right in between first and second maximas, because first maxima was at, okay, This was at, so their midpoint. So again, this is the second bright fringe. Now right in between this and this, you have the second dark fringe. So again, this distance, again the total distance between the first bright fringe and the second bright fringe, this is d lambda by d. But at the midpoint of these two, you have the second dark fringe, like that. Okay, so based on this, we define another parameter which is called the fringe width. So this should not be confused with slit width. Slit width is the width of the, the slots or the openings and the two opaque screens, which are called the slits. that is of the order of lambda, which we had seen earlier. But here we're not looking at the opaque screens. We are seeing the main screen in front, on which we are observing the bands of alternate bright and dark intensity, and or what we call the fringe pattern. So in that fringe pattern, if we according to what we've just seen, the bright and dark fringes are placed equidistant from each other. In between any two bright fringes, there's a dark fringe. In between any two dark fringes, there's a bright fringe, like that. So the fringe width is a term we define. Let's say delta W. It is the distance between consecutive bright fringes. Okay. Or you can even think of it as like consecutive dark fringes. Okay. And you can see that delta W will be nothing but d lambda by d. You can understand this because as far as the bright fringes are concerned, the position of the central maxima is 0. The position of the first maxima is plus or minus d lambda by d. The second maxima is plus or minus 2 times d lambda by d. Like this, the nth is at plus minus n times d lambda by d. So the distance between any two of them, y2 minus y1, or this or this, or in general any two, this quantity is this. Okay. Or on the other hand, we can also talk about the dark fringes, and we'll see any two consecutive dark fringes are also located at that same distance from each other. First dark fringe is at half of d lambda by 2. Second order dark fringes are at plus minus 3 by 2, plus minus 5 by 2. So nth order dark fringe is at plus minus 2n minus 1, like this. Okay. So again you can see that this thing is all equal to this one. So fringe width becomes the important parameter, because when you're actually doing the experiment, that is the thing you can measure very accurately. We use an instrument called the micrometer to measure the distance between alternate dark fringes or bright fringes, and from that we actually back calculate to calculating the wavelength of the monochromatic source or whatever else we need to in the experiment. Okay, so this is clear. So what you're seeing on that final screen is alternate bands of bright and dark light. So this here, this is the fringe width. Okay, now next very important, variation of net intensity with the position y or the angular position theta. So the concept that we use here is that for two waves of intensities I1 and I2 interfering at a point with phase difference delta phi. So by the two waves you mean two coherent waves. Okay. We had the formula that net intensity was I1 plus I2 plus 2 times square root I1 I2 cos delta phi. This is a universal formula. Okay. This could be intensity of sound waves or electromagnetic waves. In case of transverse waves, instead of intensity, we talk about the power transmitted. Okay. So basically, this formula was coming from this one. The net amplitude this. Okay. So E over here could be pressure amplitude of a pressure wave, or E could be electric field amplitude of an electromagnetic wave, whichever of the two. Okay. But intensity is proportional to square of amplitude. So when we square this equation, we get this one. Now in this, one more important special case is that if I1 is equal to I2, okay, is let's say I naught, that is the two interfering waves are of identical intensity, then we can reduce the formula for the net intensity to be 4 I naught cos square delta phi by 2. Using that formula that 1 plus cos delta phi is 2 cos square delta phi by 2. Making use of this formula, it becomes like this. So this is the one that becomes significant for us in the standard Young's double slit experiment, because in the standard experiment the slit width of S1 and S2 is the same. So S1 and S2 are allowing the same amount of intensity of light to go through. So individually they create the same intensity on the screen. So in a standard YDSE, of course we'll see some variations of that also, but in the standard version of the experiment, the slits S1 and S2 are of equal width, okay, and also they are equidistant from S. So therefore the individual intensities they produce on the screen are identical, and that we take as I naught. So we use this reduced formula, for the special case when I1 is equal to I2. Okay. So the net intensity at any point on the screen is from this formula. Now we just have to replace delta phi with the relationship of phase difference with linear position y or with angular position theta. So therefore you can see that at a point P on the screen, the net intensity is given by this above formula, 4 I naught cos square delta phi by 2. So in this formula, delta phi is 2 pi by lambda delta x, or 2 pi by lambda into y d by d. Sorry, small d by capital. Like this. So therefore, so it varies continuously. So if you look at the variation of intensity with the position, so let's say I'm picking out the y coordinate versus intensity of light like this. This is where the central maxima is. So that intensity will be a cos square graph. Symmetric on either side. These values are 4 I naught, and this is where the dark fringe is located. So it is, this is where the first bright fringe. This is where the second dark fringe is located. This is where the second bright fringe, so on and so forth. Or if you draw the graph this way, the intensity on the y-axis, y coordinate like this. You can see the intensity doesn't abruptly change from bright to dark. It changes like a cos square function, but every time you reach a position which is a multiple of d lambda by d, you reach a maxima. Whereas every time you reach an odd multiple or the midpoint between two maximas, you reach exactly that position where the intensity is tending to zero. So practically, I mean, ideally speaking, there is no net intensity at all at that position. It should be a completely dark, zero intensity kind of position. Okay. So this is the intensity versus position. So at the maximas, the intensity is 4 I naught, 4 times the intensity due to a single slit. Okay, people, so take this down and we'll take a quick break now. After that, we will come back with numerical problems with not only the standard formulae, but with a bit of variation in the experimental setup here and there, different types of adjustments of variations, or alternate versions of Young's double slit experiment can be asked, where you have to just adjust a little bit from the standard situation to understand how different kind of patterns can be observed on the screen. So the main aspect of this chapter for you, especially for JEE Advanced, there's only Young's double slit experiment in wave optics, is going to be all these variations of the standard experiment. The standard experiment is what we have studied till now with the complete description, but small little adjustments that are made to the standard setup create according adjustments to the observation from the experiment, and doing calculations based on that is the part of your syllabus. So just take a short break, we'll continue after that. Yes, should I show the Okay, students, so let's resume. So we'll start again now with a question, numerical example, which will make all the type of calculations in a standard Young's double slit experiment clear for us. So in a standard Young's double slit experiment, light of wavelength, so obviously monochromatic, 600 nanometers is used. Okay. And the distance between the two small slits is, let's say, 1 millimeter, whereas capital D from opaque screen to the main screen, that distance is 2 meters. Okay. So first of all, calculate the fringe width. So this is a direct formula based question. This is more like your the type of question you can expect at board level. Delta W. Now second, assuming the two slits S1 and S2 are of same width, if the intensity at the central maxima is, let's say, something, let's say it is 2.4 watts per meter square. Calculate intensity at any minima, the midpoint of second minima and second maxima. Okay. And okay, so just start this question, work it out all of you. Okay, so the second part of the question, these are the type of things you can expect at JEE mains level, these type of questions. So how much is the fringe width coming out to be? Just apply the formula d lambda by d. Right, very good, Ganesh, that's correct. So you'll get this directly by the formula d lambda by small d. So that is 2 into 600 nanometers. So this divided by 1 millimeter. So this will be the fringe width in meters, which when you calculate, you will see it will come out to be 1.2 into 10 raised by minus 3 meters, or 1.2 millimeters. Okay. So these are the standard type of numbers we are dealing with in experiments. Okay. Now the second thing you can see, S1 and S2 are of same width. Okay, so if they are same width, it is basically that they are creating intensity, same value I naught. So therefore, I net at any point is given by that formula I naught cos square delta phi by 2. Okay, where delta phi is this and this is this. Or so this is the concept that we have to use. Okay, so obviously you can see that this thing is going to be the maxima, and that is going to be 4 I naught. Okay, at y equal to 0. But we also know that because of this, the minima will have an intensity of 0, and that will be at y equal to plus minus half of d lambda by d, 3 by 2, and like this. So maximas of 4 I naught will be located at y equal to, you can say, n times the fringe width, where n is equal to 0, 1, 2, like this. And minimas are similarly going to be located at y equal to 2n minus 1 by 2, plus minus of course the fringe width. And here n starts from 1, 2 onwards. That is why we generally take it as 2n minus 1, because there is no such thing as 0th minima. So our index n should not start from 0 for the minima, it should start from 1. The first minima located symmetrically above and below, second minima where it becomes 3 by 2 lambda, like that. So obviously the answer to A part of second question is going to be 0. But now it comes to the interesting thing, the midpoint of second minima and second maxima. So what you have to figure out is at that point, which is the midpoint of these two positions, what our delta phi is going to be. So from that we can figure out what the net intensity is going to be. Obviously it's going to be something between 0 and 4 I naught, less than 4 I naught, greater than 0. So it's going to be less than 2.4 watts per meter square, but it's not going to be 0 at the same time, because it's not the minima point. It's in between the minima and the maxima. Second B part, Ganesh, you are getting yeah, A part is obviously 0. B part you should get 1 watt, 1.2, exactly half. Yeah, that's correct. Okay, good. Because you will see that the phase difference there will be such that cos square delta phi by 2 will come out to be half. So let's understand why that's happening. So second, A part obviously intensity is going to be 0, because at the minima I net is 0. Why? Because I1 was equal to I2 equal to I naught. So maxima had the intensity of 4 I naught and minima had the intensity of 0. Okay. But a general point, we will use this formula. I net will be 4 I naught cos square delta phi by 2. Yeah, I'll check your third answer also. Just give me a second. So at the midpoint of second minima. Now second minima में y coordinate क्या है मेरा? Let's say it's y prime. It is 3 by 2 d lambda by d. Okay. Or you can say 3 by 2 times the fringe width. And second maxima. So second maxima में let's say I'm writing the y coordinate as y double prime. So that is how much? It is 2 times d lambda by d. Or it is 2 times the fringe width. Okay. So इन दोनों का जो मिड पॉइंट होगा उस पे मेरा y कोऑर्डिनेट कितना होगा? कितना होगा, है ना? So it will be, this is like 1.5, this is 2, so it will be 1.75 times d lambda by d, or 1.75 times w, or we can write this as 7 by 4 times fringe width. Okay. Now we don't really need to substitute in complicated formula, but we can if we want. Okay, so phase difference is 2 pi by lambda into path difference. Now at this y coordinate 7 by 4 d lambda by d, what will be a path difference? It will be, say, small d into y by d. Remember, because delta x was d sine theta, so that's approximately this. So correspondingly, this will become d by d into 7 by 4 d lambda by d. So our path difference is becoming 7 by 4 lambda. So this is the proper, fundamental way of solving this. I will tell you some shortcuts also, so you don't need to do such lengthy calculation. But so at this position, at this midpoint position, our phase difference delta phi becomes 2 pi by lambda into 7 by 4 lambda. So as you can see, it becomes 7 lambda by 2. Oh, sorry, 7 pi by 2. This becomes our phase difference. So then we can use the net intensity formula. So therefore, I net will become 4 I naught cos square of half of this. Okay. So that is 4 I naught into square. So not pi by 4, pi by 2. Yeah, it should become pi by 4 only. Delta phi by, so 7 pi by 4 is cos of pi plus 3 pi by 4. That is minus cos 3 pi by 4. Or better, we can write it as this 2 pi minus pi by 4. Better. So that is cos pi by 4. That is 1 by root 2. That's how we are getting this. So it is 2 I naught. Okay. So that means the net intensity at that point will be half of the maxima. It is half of 4 I naught now. That is half of the central maximas. So that's why, okay, this will be the full solution of it. Okay. But like I said, here I've done a lot of calculation because I've just gone with the formula method. Now we can use some logical shortcut steps and avoid such lengthy calculations. You can do this much faster. So I'll express that also for you. Yeah, third one, Ganesh. I'm looking for the answer. Ashish, your answer is zero point 0.6. Okay, seems correct. I think it become half square times. So yes. Yeah, I'll show the third question. You have to find the net intensity at y equal to 4 millimeters exactly. And the third, I mean the second question, C part, wanted to find net intensity at y equal to this much 4.0 millimeters. So this is the data you require. Yes, Ninad, that's correct. Ninad and Ashish, both of your answers are correct. Very good. Yes, Ganesh, that's correct. Zero point 0.6 is the correct answer. Okay, now see, before I come to the full calculation of the C part, I will explain to you how we can really simplify these calculations of phase difference from Y. So for that, what we have to understand is that the relationship between path difference and Y is a direct proportionality. And delta X is equal to Y d by d. Okay? And the relationship between phase difference and path difference is also a direct proportionality. Delta phi is equal to 2 pi by lambda delta X. Okay. So you can see that if you see, we can understand it this way that for Y equal to one fringe width, that is d lambda by d, the corresponding path difference becomes one full wavelength, and the corresponding phase difference becomes one full phase of 2 pi. Okay. And since there's proportionality, so therefore, for y equal to any number times delta w, that is the fringe width, that is n times, what will happen? Corresponding delta x will become that same number times lambda, and phase difference will be that same number times 2 pi. So here n is any real number. So you can use that concept. So for example, if we are at y equal to, let's say whatever 2.6 times the fringe width. So what will be the phase difference at that point? The phase difference will be 2.6 times 2 pi. We can just directly say this from ratio and proportionality, because if you go with the full calculation, you will realize that if y is at this thing, it means that y is equal to 2.6 into d lambda by d. So correspondingly, delta x is this. So you realize from this that it will be So it will be 2.6 lambda. So phase difference will be, so that will become this. Okay. But this whole cycle of calculation we don't need to do, because we understand that there is this proportionality. We understand that delta x upon lambda is the same thing as delta phi upon 2 pi is the same thing as y upon this proportionality, because this is proportional to this and this is proportional to this. So this is a very effective way. So for example, the second question's B part, we want the midpoint of second minima and second maxima. So you can directly understand that at the second minima, my phase difference is going to be how much? It's going to be 3 pi. And at second maxima, my phase difference is going to be how much? It's going to be 4 pi. So at the midpoint, okay, because it's proportional, na? Phase difference is proportional to. So you can see delta phi is directly proportional to y. So it's going to be just delta phi 1 plus delta phi 2 by 2. So it's going to be 7 by 2. So you can skip all those steps and just directly do it. Now similarly, we can also do the C part, which I'll come to. Okay, but just make a note of this thing first. This is very important. Okay, this part here. So finally, this relation, that if your position on the screen is some multiple of delta w, or the fringe width, then at that position your phase difference is the same multiple of 2 pi. It's very simple. There's any factor into the fringe width, so it's that same factor into 2 pi. The phase difference will become the same factor into 2 pi. So if you just apply this shortcut trick to doing these type of problems, you will see that you can do the JEE mains or single option MCQ type of questions very fast. It's not just that it's a easy topic, but you can actually develop some tricks to save a lot of time in questions from wave optics. So it becomes doubly scoring, because that time saved you can invest in other questions. Okay, so if we come to the C part of question 2, it says we want to find the net intensity at a distance of 4 millimeters on the screen from central maxima. And we've already seen that delta W, the fringe width, we had already calculated this. This was equal to 1.2 millimeters. So you can see that my Y, which is equal to 4 millimeters, is equal to 4 upon 1.2 times the fringe width. So that is 40 by 12, or 10 by 3. So 3.33, or 10 by 3 times delta W. So at this position, at y equal to 4 millimeters, what will happen? My phase difference delta phi, I can directly say it will be 3.33 into 2 pi, or 10 by 3. Okay, so my net intensity is going to be 4 I naught cos square of 10 pi by 3. That's it. Now we're done. So we can see that cos of 10 pi by 3, you can write as cos of 2 pi plus, sorry, 3 pi plus, yeah, so plus pi by 3. No? So that is minus cos pi by 3. So that is minus half. Okay. So cos of 10 pi by 3. So all we need to do is substitute this here. So it is 4 I naught cos square. Achha, so okay. So it is I naught by this. That means basically it is the maxima by 4. Okay. Because 4 I naught was the intensity of the maxima. So in this case it becomes whatever 0.6 watts per meter square. Okay. So here also I have explained in detail, but at the exam level, all you need to really worry is about the this thing. My position y is some kind of factor into fringe width. So what is that factor? From that factor, I directly know what is the phase difference. So all you need to really think is, okay, y is 4 millimeter. The fringe width was 1.2 millimeters. So y is how much? It is 10 by 3 times the fringe width. Therefore, phase difference is 10 by 3 times 2 pi. So that's it. And then you know the formula. Then substitute that. So you have to be time efficient in solving these type of questions, and this is the easiest way to be time efficient. Understand the proportionality between path, position, and phase. Yeah, in variations also it will work, Ganesh, as long as we can use the approximation that sine theta is tan theta. So your path difference is directly proportional to y. It will work in that. Okay. And in any variation of YDSC, we have to have that thing in place. That capital D is very large compared to small d. So we are always dealing with small angles. Okay. So what happens if if we lose that proportionality? If suppose we take an example of YDSC where like here only, let's say instead of small d being 1 millimeter, suppose we had bumped up small d to let's say 10 centimeters. See what will happen to our fringe width. It will become so narrow that it's nearly invisible. But more important than that, our approximation that sine theta is equal to tan theta will become less and less true. So what our calculation is telling us will vary more and more with respect to what the experiment will show. Okay. That is the point you have to understand. So whether you are practically executing this experiment or you're doing theoretical calculations while like we're doing here, it is crucial that the experiment has that thing in place, that capital D should be many orders of magnitude larger than small d, so that d by d is very small compared to 1. So accordingly, y by d is also very small compared to 1. So sine theta becomes tan theta. Okay, so this is this. Now let's start looking at the variations. So one important, very standard type of variation of YDSC is where we put, what is called a slab, a refracting slab in front of one of the slits. So that slab slows down the light because it's like it's transparent, but it's also refractive, which means speed of light is less in that. Okay. So if this is the middle opaque screen, and this is the main screen. Okay. So the most common type of variation question is the effect of a refracting slab in front of one of these. So the effect is in two things. One is that, of course, the slab ends up absorbing a bit of the intensity of light. So I1 is no longer equal to I2. So that changes the relationship between I maximum and I minimum and all that. But more importantly, it changes the location of the maximas and minimas. Okay. So a refracting transparent slab in front of one of the slits only. Okay. This is a very common type of example. So now what happens is, even at the central position, you can see that there is some path difference between light. So if you imagine two beams of light which are coming parallel to the symmetry axis also, they will have some path difference because the light has slowed down inside. So whether you're looking at the central maxima or any other point, you can see at the central maxima, of course, the light is like this, but it's nearly parallel because you have to imagine that capital D is much larger compared to small d. Not like actually I've shown in my diagram. Nice, many orders of, okay. So you'll see that the slab creates a phase difference because light travels slower inside the refracting medium of the slab. So let's say the slab has a thickness of T and it is made of material of refractive index mu. So how do we understand how much phase difference is creating? And therefore, as a result of that, how the fringe pattern will shift. So because it creates a phase difference, the fringe pattern shifts. Okay. So this point, the central maxima is no longer at O. Okay. In fact, at the position O, light from S1 is behind in time because it's the path is the same. S1O is equal to S2, but in between light from S1 has slowed down to B equal to C by mu inside the slab. So it's reaching behind in phase. So the phase difference at O is no longer zero. So in fact, you will see that the central maxima will shift to some position above O. Okay, so that the light takes a longer path from S2. So to compensate for the fact that light is traveling slower from S1 when it's going through the slab. That also we'll see how to do that calculation. So in fact, central maxima will shift to a point at positive y from central maximum, from the symmetry point. It will shift to a point at a positive y coordinate here. Because I put the slab on the top slit, not on the below slit. So the central maxima will shift to some point above or not below. Okay, so written this down. Now let's see how we'll do the calculation. So let's understand the property of the slab first. Okay, so supposing we have this situation, we have the slab of thickness t and refractive index mu, and we have light coming from a very distant monochromatic source. So at these positions, the phase difference is zero. But now, if you look at this position, there is some phase difference between the two beams. Okay, here the phase difference will be zero. Why? Because okay, now see, if I denote this position as x equal to 0 and correspondingly this position at x equal to 0, and I take this as my x-axis. So for beam 1 and beam 2, so this position correspondingly now becomes x equal to t, which is the thickness. Okay, so for beam 1, from x equal to 0 to x equal to that thickness, the equation of the variation of electric field will be like this, let's say, where k prime is 2 pi by some lambda prime. Lambda is the wavelength of light in air. So lambda prime will be lambda by mu. Why? Because inside the medium, the refractive medium, V is equal to C by mu. Okay. So from that, we have the relation that F is equal to the frequency is equal to C by lambda is equal to V by lambda prime. So inside the medium, the wavelength has changed to this. So accordingly, the phase constant has changed to this. Whereas for beam 2, from x equal to 0, x equal to t, like this, where k is equal to 2 pi by lambda. This is in air. Whereas k prime is in glass or whatever medium, which has a refractive index mu. Okay. So you can see the phase difference that is developed between this and this. This phase difference now is the difference of these two. So it is k minus k prime into thickness. This is the phase difference at x equal to t, with the phase difference that is developed. So that is 2 pi by lambda minus 2 pi by lambda prime into the thickness. So you can even take 2 pi by lambda common. This is the phase difference. That is. Just make a note of this. So had they been both been traveling through air for that distance t, or both been traveling through the same medium like glass through the distance t, they would have had no phase difference by the time they reach from x equal to 0 to x equal to t. But because one is traveling inside glass or whatever medium, okay, and the other is traveling through air, the fact that the one in glass has been slower, so its speed has become c by lambda. So that means its wavelength has changed from lambda times, sorry, c by mu. So its wavelength has changed to c by mu, because frequency is independent of medium. That is the important thing. Yes, that also we can do. Yes, Ganesh, that's correct. You can also consider the path difference as so many times the time difference, and the time has increased while going through this slab. It is omega into time difference. You can also think of it like this. So delta t is the difference in time to travel to a distance t inside glass versus air. So that is, when you do this calculation also, you'll see you'll get this. But one important thing to understand amidst all of this is that wavelength lambda and propagation speed b are affected by the medium. That is why lambda prime becomes lambda in air divided by mu. Speed becomes speed in air or vacuum divided by mu. But frequency is independent, because after all it's a wave phenomena. And just as a general knowledge thing, you should know that the perception of color of light for us is as per wavelength and not frequency. So that is why the same beam of light or the same source of light will appear to be a different color when we view it underwater compared to when we view it outside water. Because the wavelength of that same beam that we are seeing underwater is going to be different compared to the wavelength we are seeing in air or vacuum. So the color that we perceive, yeah, physiological response to light, color is dependent on wavelength, and wavelength does depend on medium. So now, just to make the calculations for these kind of things, calculating phase difference because of difference in medium and all this easier, we introduce a parameter called optical path length. So this is like a trick method or an equivalence method that makes it easy to do these calculations. So optical path length, let's understand this. So when light or any EM wave for that matter travels a path length of, let's say, x inside a medium of refractive index mu, okay, the equivalent path traveled in free space, that is what we call its optical path length, x optical, like this. Okay. So because it would have traveled in free space at speed c, whereas here it has traveled inside a medium at speed v equal to c by v. Okay. So x by v should be equal to the equivalent optical path length divided by c. So that gives us the formula that the optical path length is, it is like the equivalent amount of path length in air. It's traveling slower inside a medium, so you can say that it's traveling equivalently a longer distance if you are measuring in terms of how much distance it would have traveled in air in that much time. So This is a very important concept, and then the formula from that concept. Just make a note of this. Then we'll see that solving that type of problem with the YDSC variation becomes very easy with this. Okay, so now see, it becomes so easy to visualize these type of variation problems. So coming back to that YDSC problem, YDSC with a slab in front of one of the slits. So in this variation, yeah, in this variation, right? So in front, at the symmetry point, what is happening is that the light that is coming, it's more or less parallel to the principal axis. That we're not able to show in this diagram because we can't really show something which is several meters, but this light is more or less like this. It's parallel to the principal axis. So the light reaching at O, the geometrical path length x1 is equal to x2, which is more or less equal to capital T. Okay. But the optical path length is slightly different. It is d minus t plus tb, like this. Because it's traveled a distance of d minus t through air. But okay, so this is from S1, whereas from S2 the optical path length is equal to d only. So hope this point is clear to all of you. So we can say that the phase difference of light reaching at O, or we can even introduce the term optical path difference. Okay, the optical path difference at O, that is becoming just mu minus 1. into the thickness. It's just this thing minus this thing. It is x1 optical minus x2 optical. That thing is mu minus 1 into the thickness of the slab. Okay. So if this mu minus 1 into t is equal to some multiple of d lambda by d, or the fringe width, then phase difference delta phi, which will become 2 pi by lambda into optical path difference, then phase difference delta phi will become n times 2 pi at O. Okay. And therefore the central maxima will shift to a point above where actually the distance yc will be that same n times the fringe width. But I'll explain why that happens also. So first of all, what will happen at the symmetry point O? We won't have the central maxima. Okay. So central maxima has shifted to C at y equal to yc with respect to O. And at O, we have this, the phase difference of this much. So that is what's happening at the central position. At the symmetry position O, there's no longer the central maxima. In fact, there's a phase difference of this much, where that delta x optical is mu minus 1 into the thickness. But at the same time, at the central maxima C, what is happening? My phase difference should be 0. Okay. So that means the optical path length from O should be equal to the optical path length from 2. Okay. So the optical path difference should be 0. Okay. So now at this point, you can see the light coming from 1 is traveling a larger optical path difference, path length of mu minus 1. But the light traveling from 2 is traveling a longer distance now. So that distance is how much? D sine theta. So this term should become 0. Or that is D into yc by capital. So the central maxima C is at y equal to this y quadrant of the central maxima, which is mu minus 1 into this thickness times capital D by. So it does not really depend on wavelength, because central maxima, it depends on the thickness and the refractive index of the slab. Make mu equal to 1 and it's back to 0. And of course, the other thing is the fringe width delta W still remains d lambda by d. And this is not affected by the slab. It's only the position of the fringes which is affected. So basically what happens is, compared to the standard YDAC with the slab present, compared to standard YDAC for this experiment, the entire fringe pattern has shifted by delta y equal to yc above from the original. Like just the entire pattern, you have shifted it up from the position O to the position YC, okay, with that capital N number of fringes shifted up, okay, where that capital N is nothing but mu minus 1 into T by delta W. So if that capital N is, let's say, 500.56, so it means 500.56 fringes have shifted up like that. So for example, if we had that situation where d lambda by d was 1.2 millimeters, like we had seen there, okay, and the thickness of the slab we are taking is sorry, this is upon lambda, not W. The thickness of the slab, so lambda was 600 nanometers, and the thickness of the slab is, let us say, 20 micrometers, and the refractive index is 1.6. Okay. So you'll see that mu minus 1 into thickness is 0.6 into 20 into 10 raised power minus 6. So that is how much? 1.2 into 10 raised power minus 5 meters. Okay. So compared with lambda, you can see n is equal to, okay, so that is 20. Okay. So n is 20. So it has shifted by 20 fringes. So in this case, the central maxima has gone 20 fringes up with respect to O, or the coordinate of the central maxima would be 20 times the fringe width, 24 millimeters. That would be the position of the central maxima. Okay, so again, these type of calculations become easy to do by using the proportionality concepts that we had discussed earlier between path, position, and phase. That is this thing, that y by delta W is equal to x by lambda, delta x by lambda is equal to delta phi by 2 pi. This proportionality always works as long as capital D is very large compared to small d. No, Sushruta, I have already explained that point. The frequency of light inside the medium does not change. It's the wavelength which changes. And that is the fundamental principle of waves that continues from mechanical waves that we had learned earlier. That frequency of oscillation, in this case it is the oscillation of electromagnetic fields, is independent of the medium properties. It only depends on the source. Whereas the propagation speed and lambda, these two things are affected. Okay. So what happens is lambda changes to lambda prime, P changes to this, okay, but frequency remains the same inside any refracting medium. Okay, so hope this point is clear, Sushruta. Okay, very good. So this is something important you should remember. Okay. All right, people. So we will conclude today's session here, and really, I mean, this is most of the type of tricks that you need to do your JE advanced as well as mains levels questions for YDSC we have covered here. Now, H.C. Verma has a very good set of focus problems in this chapter, wave optics. So if you cover H.C. Verma A to Z, you're basically almost done. A few extra type of questions in diffraction and all we will see, but most type of questions, I mean more than 99% type of questions for JE advanced, you will cover by doing HC Verma itself. So, and plus it's a very good set of questions. It will give you all types of practice from basic to complicated things. So you can target that in the next week. It will not take too much time for you to solve also. Just revise through my lecture. Okay. Yeah, I will send you the notes very soon by today itself. Don't worry. Plus, this optical path length concept is explained in Resnick Halliday as well as in HC Verma in very short. or if you see solved examples in HC Verma, they will use the same kind of methods that we've done for these questions. Okay, so you can do that also. You can go through the illustrated examples and okay, then straight away come to the questions after revising my notes. Okay. So that's it for today's class, people. Thanks for attending. Wish you all the best.